So today let's explore these questionable power supplies. They came with a Wi-Fi router, but the problem is they don't fit into our socket, and also there is a big question mark whether these are safe to use or not. And because of that my friend ended up buying some more trustworthy ones and donated these for analysis. And let's take a look at them. The input is basically universal mains and the output 12 volts 1 amp. It used to have a center positive connector before it was cut, and 2401. I guess it's a date code 2024 January, or the first week. So these are quite recent, not old. Let's just horribly botch some USB connector on it. Then I can plug a USB tester into this and a test load. And this of course has to go into a dodgy travel adapter. 12 volts. Let's try to load it. Increasing the loading current on the test load. It can do about 1.29 amps. That's the maximum current. Then the voltage drops. But now of course let's try to open it. No screws, so... And that's it. Now let's explore the internals closer. It actually doesn't look as bad as I expected. You can see the mains comes in through these contacts into these contacts on the board. Then the mains goes via a fusible resistor, working as a fuse and limiting the inrush current. Then that's the first capacitor, then a micro 400 volts, the smoothing on the primary side. Then the positive goes via one inductor and the negative via another inductor, a different one. And then another smoothing capacitor on the primary side. I guess this resistor is fusible, so it should have some fire safety. There is inrush current limitation, there is interference suppression in these inductors, and a pair of capacitors instead of just one, and having the inductors in between, it effectively suppresses the differential mode interference. But even a common mode interference, going back into mains, having inductors in both sides, both in positive and negative. There is some auxiliary capacitor, low voltage capacitor, for the low voltage for the chip. And here's the transformer, the secondary side capacitor at the output, and on this side you can see the bridge rectifier, couple SMD resistors, a capacitor, the primary switching chip. There is no discrete transistor, some diodes, probably in a snubber network, and rectification of the auxiliary winding, I guess. The small one probably rectifies the auxiliary and it goes into this capacitor to generate a small low voltage for the chip, and there is actually a very nice big isolation distance between the primary and secondary side. This really doesn't look bad. There's a diode rectifying the secondary and going into this capacitor. There is also some loading resistor here, and this is the snubber network for the diode, which is often omitted but not here. And looking from top, there is a space for a metal oxide resistor for overvoltage protection right after the fusible resistor, and this is omitted here. There is also an omitted Y1 capacitor between the primary and secondary side. This one typically is to suppress the interference, the common mode interference going to the output. And also at the output there is just one capacitor instead of two capacitors and an inductor in between to suppress the differential mode interference or the ripple. So it seems the interference going back to mains is suppressed sufficiently, but not so much the interference going to the output. But on the other hand, the transformer looks nice so far. It has this extended section, bringing the pins of the secondary farther from the other windings for better isolation, for more safety, so the mains doesn't get to the output. The transformer is cracked here, isn't it? Of course, there is no reason not to open the other one, so I opened it as well, and it looks identical, except that in this one the transformer is not cracked. In this one it is. Let's remove the insulation around it to see it better. It's broken here, and the pin actually barely makes it into the board. In the other one the pin is protruding farther. In this one it's probably barely touching this solder joint. And I probably know what happened here. They were pushing the transformer into the board and the pin didn't align with the hole, and they forced it and actually cracked this bobbin. Well, it has to be making contact. This is the one I tested, but it's making contact just barely, I guess. Let's try to desolder the transformer and see. It's always better to plug your soldering gun in. It is actually soldered a little bit. And the board without the transformer, here seems to be a date code 2023, week 49. So the board is made about 1 month before the entire power supply. Week 49 has to be the beginning of December. Here's the transformer. The secondary seems to have a safety insulated or triple insulated secondary, which is nice, except it's broken here. And the pins are farther from the other windings for more safety. Now let's try to further open it. And there is actually a wire connecting the slightly conductive ferrite core to the positive of the primary side. It seems this one has no high frequency voltage on it, so it's to stop the interference from radiating from the ferrite core, because otherwise the high frequency is coupled capacitively from the windings into the core, and then this works as an antenna and radiates it. This piece was actually a continuation of the primary winding. Now of course the melted hair dryer. Then the ferrite core separates, of course. It's a low power supply, just 12 watts, so it's a flyback, and the core has an air gap in the middle. Removing this tape and the secondary here. It seems to have enough insulation under it, but also enough insulation on it, not just the lacquer, but a much thicker insulation for safety. 2 turns, 3, 8, 9 turns. And the autopsy of the insulation on it. There is the clear insulation on top, then the yellow one under it, which is not easy to remove, and then the wire with maybe the lacquer on it. So I guess it's triple insulated, or at least 2 layers of insulation, each of them much thicker than the typical lacquer, but under it still a good insulation, a good tape. 1 layer, 2 layers, and then this winding, which has a loose end. Is it the shield? It has 1 turn, 2, just 2 turns, and then it goes to this pin, the negative of the primary side, the cold end of the auxiliary. And from this pin also the auxiliary continues. 1, 2, 9, 10 turns, going to this pin. And no gaps in the insulation, but the insulation between the primary and auxiliary isn't critical. It's both on the primary side. 1 layer, 2 layers, 3 layers. For some reason, and then the primary here. 1, 2, 40, 70, 78. And of course measuring the diameters of everything. And here's the reverse engineered transformer. And besides the transformer, I decided to reverse engineer the full schematic. The mains comes in here via this fusible resistor, the omitted metal oxide resistor here, the bridge rectifier, the first smoothing capacitor, the interference inductors, and the second smoothing capacitor. Here's the transformer, its primary, with the snubber network. Here's the switching chip, the startup resistors powering it initially, and then it's powered using the auxiliary winding, and the supply pin has a capacitor on it, the 0 volt pin. Here's the current sensing pin with the current sensing resistors, and the feedback pin to sense the voltage on the auxiliary winding, the upper resistor in the divider, the lower one made of 2 parallel, and a low capacitance capacitor, which in combination with this resistor works as a low pass filter. And the high voltage switching transistor in the chip goes from these 2 pins into this pin. Here's the collector or drain, and here's the emitter or source. Here's the omitted Y1 capacitor, and the secondary is rectified using a Schottky diode with a snubber network, this smoothing capacitor, a loading discharging resistor, and the output, and that's it. And there is no optocoupler and no secondary side voltage sensing, because it's using the auxiliary winding for the voltage sensing. And there is no Y capacitor, but the interference at the output still might not be that bad, because the auxiliary is between the primary and the secondary, so it basically works as a shield, because the primary has by far the highest high frequency voltage on it. The secondary is shielded from it using the auxiliary with a low voltage on it, plus this shield winding, which basically goes the other way and cancels out the high frequency voltage on this side. So it's possible that this transformer design complies with interference regulations even without this capacitor. And the secondary waveform at full load, it's running at about 54 kHz, and gradually reducing the load, it reduces the frequency. I zoomed out the time base, and full load again, and reducing the load. No load. And the output ripple at full load, AC only, it's about 160 mV peak to peak. and reducing the load. And also how the output ripple correlates to the secondary waveform. The ripple waveform is basically copying the waveform of the current in the Schottky diode on the secondary side. And here's the ringing, so it's running in a discontinuous conduction mode. I've put the cover back on, let's leave it running for a bit longer. After 2 hours, no failure. And some quick thermal imaging from the outside, about 56 degrees. Nothing bad. And let's take the cover off, and about 107 degrees Celsius, the hottest part, which is the chip here. And the board under the chip. The transformer is about 87 degrees. Let's put the macro lens on. Here's the chip. Nothing else super hot here. Well, this resistor in the primary snubber network is hot. Of course, the secondary Schottky is also going to be a bit hot. And the electrolytic capacitors. And the secondary electrolytic capacitor. At full load it's hot, but not in a way that it would self-destruct. And here's the datasheet of the chip in it, and some example schematic. Some resistors in it have a not so human readable marking. 2 numbers and a letter. For example, 48C means 30.9 kiloohms, 1%. You can use my online calculator for this. And you can use the other calculator, which I called the calculator, to calculate that 1.8 ohms and 1.5 ohms in parallel give you about 0.8 ohms. So that's these chargers. Really not bad unless your pin misses the hole. Maybe some interference at the output, but that's the case in a lot of switching power supplies. But of course a Wi-Fi router works at a couple gigahertz. It's really not sensitive to a switching power supply noise. And one pin of this travel adapter actually went in as I pushed it into the socket. That's nice. And if you like my videos, please consider subscribing, supporting my channel on Patreon, or using the thanks button in proportion to the value you receive from my videos. And a big thanks to all of you who already support me, because this channel couldn't exist without you.